One type of measurement that EBSD is uniquely suited for is the measurement of misorientation and boundaries. This is just a list of the different types of boundaries that can be analyzed with OIM analysis, and I'll go through a number of these with subsequent slides. But because we've collected the orientation data on a point-by-point basis, we're able to represent the change in misorientation across pixels with numerous different visualizations. The first and most common is what's termed a rotation angle boundary. This is the fundamental boundary type, where we essentially shade a pixel by the misorientation, the angular misorientation between 2 points. So in this example here, we've created 4 different ranges, misorientations between 3 to 6 degrees, 6 to 9, 9 and 15, and 15 and 180. Each range can have its own color and thickness assigned to it. You can see as we draw the boundary, we see it visually. We also get numerical statistics of the fraction number and grain boundary length present of each of these types. It's important to note that the software does have a minimum boundary threshold, typically 2 degrees, but that's something that can be adjusted. That's done here under Settings Preferences, where there's a setting for minimum boundary misorientation. When we adjust that, this value in these statistics will also change based relative to the number of boundaries that are then counted. In addition, when we're drawing boundary segments, even if we have a range that we've defined manually below this threshold will supersede that and will only draw boundary segments that exceed the minimum boundary misorientation as shown here. So if you try to do this and you don't see the boundaries you're trying to define, this is where you probably should look. This is setting the minimum boundary misorientation threshold to 1/2 degree, and then we start to see where those boundaries are located within the microstructure. The next type of boundary are what are termed axis angle pairs. In this case, we specify not only the rotation angle, but also the axis. We call that an axis angle pair. And we define the crystallographic direction that's used for the rotation, the angular amount of that rotation, and then the tolerance from the perfect alignment of that misorientation. So for example, if we wanted to do a twin, which is a 60-degree rotation, about a 1-1 axis in something like an FCC material, we also have to specify how close do we want that to be. So in this case here, we see the rotation angle boundary is just set to a 60-degree rotation angle with plus or minus 5 degrees. The axis is based on a rotation of a 1-1 crystal orientation, a rotation about the 1-1 crystal direction, I mean to say, and within 5 degrees of each other. And then we can align those as pairs as an axis angle pair to enforce both of those requirements on the boundary type. We can also show grain boundaries. If you remember from the video on the grain definition and grain tolerance angle, however those grains are determined, we can then draw the grain boundaries. Same thing with phases. We can draw a line between identified phases in the microstructure. We can also show grain shape ellipses, where for each grain that's been detected, we fit an ellipse. This is important because we can then look at some shape aspect ratio information for the ellipses to see if there's any directionality alignment of these. It's important to note when we do this, it works best for grains that are not touching the edges of the scan area. Those are really incomplete grains, so we want to be a little bit more careful how we analyze that. This is just an example of some shaped grain ellipses fit to this microstructure. You can see when we do this, we're able to identify the major axis and the minor axis. The grain shape aspect ratio is the length of the minor axis divided by the length of the major axis, and we can plot that out and visualize how that aspect ratio is distributed within the microstructure. And then the grain shape orientation measurement refers to the angle of the major axis relative to the horizontal. So again, if you have grains growing horizontally or vertically, you can numerically extract that information. We can also identify plane traces. These are a set of line corresponding to the trace of user-specified plane in each grain. And so the length of the trace corresponds to the inclination of the plane, and by that, the shorter the trace, the closer the plane is aligned to the sample surface. And we can draw plane traces or plane normals. These are just some examples from the 101 plane trace in the cubic beta phase, and the 001 plane trace from the hexagonal alpha phase, and these different grains. And we can see how they can be used to visualize how these orientations are aligned spatially in the grains, and also to compare as we go across grain and phase boundaries how certain planes may have an alignment. The other thing we're able to do, of course, is we measure the data on a grid. We can fit what we call reconstructed boundaries to fit a line segments to the measurement. So it's able to minimize the effects of measuring on a grid. And so we do this in two different ways: reconstructed and reconstructed twins. So for the reconstructed boundaries, we essentially find the triple points, draw a line between the triple points, and whenever the line deviates too much, we break it into smaller segments. Reconstructed twins follow the same thing, but we can also look at the misorientation relationship as well as the twin boundary plane alignment rules to enforce if we think a reconstructed boundary is a twin boundary. And you can see here from these schematics here from a paper written by Stuart Wright, coherent twin boundaries can often be differentiated from incoherent twin boundaries by looking for the alignment of the boundary trace normal with the coincident planes when they're lined up. You can kind of think that that's a coherent boundary. When the trace is not aligned with the coincident plane, it's an incoherent boundary. How does this work? We group things into grains. Oftentimes we do some sort of a cleanup just to get rid of stray points and noise. We then take the boundary segments here, and you can see here, we can see the grid relationship here. We identify the triple junctions, and then we draw straight lines between them. And in areas, here's an example where the straight line doesn't match the orientations, it will break that into a segment. And that leads into how we can also look at these boundaries into charts. And you can see there's a numerous range of charts, but all these different types of boundary charts, we can also measure them numerically and calculate the fraction of different boundary types to help compare and contrast these boundary measurements.